We had the sky up there, all speckled with stars, and we used to lay on our backs and look up at them and discuss about whether they was made or they just happened. Mark Twain, Huckleberry Finn. Which is a good quote for today's module on sky dances. And I'm here with Professor Sarah Walker, and we're going to chat a little bit about some of those sky dances. So Sarah, there's a couple of questions we want to try and hit today. One of them will be, what does the sky look like at night? Why do some stars never rise or set? What are those called, and when do they happen? And then how come we see different constellations at different times of the year? Sometimes we see different constellations in the winter versus the summer, and sort of what's the cause of that? So how many stars can one see in a night?
Yeah, so, well, if you're lucky and you're in a really dark area, you can see about 6,000 stars
6,000
on a given night, which sounds like a lot, but we know now with modern science and our huge telescopes that there's a lot more out there. But for the ancients, that's all they saw of our entire universe, was just these 6,000 stars at night.
We're here in Phoenix. How many, which is a modern megapolis, right? So how many stars do you think we can see in a big city like that?
Considerably
I don't know.
less. I'm actually, I'm quite disappointed when I look at the sky at night that I don't see all my favorites. So I used to live in New Hampshire, and you could see, it was really dark there. You could see the Milky Way at night, and it was just spectacular. But here, I'm lucky if I see Orion or, some of the stars in the Big Dipper, the really prominent ones.
Right.
But those are still exciting. So
Yeah, still
at least
cool.
I can see those.
Cool. So speaking of the Big Dipper, where did those come from? How come people made up constellations and stuff along those lines?
So it's really interesting because people have obviously been looking at the sky for thousands and thousands of years, and they started to notice that there were patterns in the night sky and would tell stories according to those patterns. But those stories actually became incredibly useful because the stars could be used as sources of navigation, or they would foretell changing seasons so that they would know if the weather was going to change or things like that, that they became predictable according to the patterns that they saw in the sky. And so it was actually really necessary to survival to understand these patterns that we saw in the heavens.
It's kind of like the great celestial book in the sky that was not erasable in that sense. So cool.
Very predictable, right? So very unlike Earth down here, where things are very chaotic. The sphere is very regular.
Very regular.
The celestial sphere.
Didn't change much.
Yeah.
So Sarah, you mentioned the celestial sphere. When you were there. You want to talk a little bit about the celestial sphere?
So the celestial sphere is really a useful conceptual tool for thinking about the night sky. So we know that all the stars are actually different distances away now, but when we look at our night sky, it looks like they're about the same distance away because they're so far away that we really can't see the distances with our naked eye. So we have this idea that all of these stars are kind of laying on this giant sphere circling the Earth.
So like sticky dots on the sphere.
Yeah, a lot like sticky dots. Sometimes when I visualize it, I think of it as holes in the sphere, and there's some light shining through behind it.
Great cosmic colander.
Yeah, something like that. So, so there's different ways of trying to conceptualize these things, but that becomes a really useful tool for thinking about the motions of the stars in our night sky, because now we can think about this great celestial sphere rotating around the Earth, even though we know that the Earth is actually what's moving.
Correct. So are there sort of like celestial guideposts or key things on the celestial sphere that mark off? Yeah,
so we can use a celestial North Pole, basically, which is the point that's directly above the Earth's North Pole, so it doesn't move relative to the Earth, and the celestial sphere rotates around it. And we also know about the ecliptic plane, which is the plane that the Earth and the Sun are in. And that acts as a guidepost for thinking about the direction of motion of the celestial sphere.
You mentioned the ecliptic, which is the path that the Sun and the planets orbit the Sun in. And so on the night sky, all those planets and the Sun look like they're on the same plane. Yes. So are there particular constellations that the Seven Wanderers happen to go through?
Yeah, so our Seven Wanderers, our neighboring planets, all have these interesting motions on the sky. Oh, yeah, so the Seven Wanderers are the names that we have for the planets in our own solar system. And they're called wanderers because if we think about the celestial sphere, the stars have very regular motions in our night sky. But then there were a few oddball stars to the ancients that kind of wandered across that pattern, and they didn't do the things that all the other stars in the sky were doing. And today we know that those are planets, and their motions are different because they're local to us. They're basically our neighbors, and they're orbiting the sun just like we are. But to the ancients, they just looked like very odd stars, and so they gave them special names, and they named them after gods even.
And we still have those names with us today.
Yes, yes.
Right? This is why we have 7 days of the week.
That's right.
For the 7 wonders. And so each day is denoted to a planet. For example, Friday is Freya's day.
Yeah.
And our names come from the North Celtic barbarians, actually, from invading Rome is where we take the names from.
Yes.
So that's where that comes from.
So all these influences from astronomy in our daily lives we don't even know about.
Absolutely, absolutely. And we'll cover a few of those. So as these planets orbit the sun, these 7 wanders, do they pass through any constellation in the celestial sphere, or are there only certain ones?
Yeah, so there's actually certain ones. So we mentioned the ecliptic plane, which is where all the planets and the sun are located. And all of that, from our perspective on Earth, all the planets and the sun actually pass through only a small number of constellations in our night sky. And those are actually the zodiac signs. And we usually think about there being 12 zodiac signs associated with each month of the year. So I'm Cancer, for example.
I'm a Gemini.
Yeah. So apparently I'm supposed to be crabby. I'm not sure if that plays out in practice, but I'm a crabby zodiac sign. But it turns out actually that there's 13 constellations.
Really?
Yes. And so there's an extra one, Ophiuchus. Is that how you pronounce that actually?
Ophiuchus.
Ophiuchus, yeah. So there's an extra one, Ophiuchus. And so some people have actually, made claims to revolutionize astrology by adding that zodiac sign.
So 12, that's a curious number.
It is.
Because we have 12 hours a day, 12 hours at night, we have 12 months,
so
12
it's not surprising
signs of
they
the zodiac.
cut that extra 13th one out to make everything symmetric.
Right, and that day there is the Babylonians.
Yeah.
It's the Babylonians where we get sort of this base 12
Right.
counting system, and we'll come back to that a little bit
Yeah,
later.
and you can really see with those kind of stories how they were really treating this sort of in a scientific way, these patterns in the sky, and trying to understand sort of their regularities, and that maybe they might have thought about 12 and 12 and 12 as being sort of a consistent pattern that became predictable.
How many constellations are there, and who
There's
gets to decide those?
I don't.
88.
88. Thank you. I know I was going to say 86. I'm like, wait a minute. Yeah. So nowadays there's 86 constellations, and they're not actually associated with patterns in the night sky. They're actually associated with regions in the night sky.
Okay.
Where particular patterns that the ancients might have recognized as being a mythical creature or something might have been in the night sky.
Cool.
Yes.
So you had mentioned that you were in New Hampshire,
Yes.
And you could see the stars, and you could see this band of light, the Milky Way. So the sun is out here sort of in the suburbs of the Milky Way galaxy.
Yes.
And, can you describe a little bit what we see depending on which direction we look in, and why do we see that band of light?
Yeah, so the Milky Way is our home galaxy, and it's basically shaped a little bit like a pancake. It's a flat disk, but it bulges in the center, so there's a lot more stars in the center of the galaxy. And like you said, we're out here in the suburbs in this nice area without quite as much radiation and all those other things. So we're quite happy where we live. But it's really interesting where we live in our galaxy, because when we look out at night and we look in different directions, we actually see different parts of our galaxy. So if we look into the bulge, we see that band of the Milky Way on our night sky. And it's actually really spectacular. If you ever have the chance to see it, I recommend it to everyone in this class, that they should try at some point in their life to go out and see the Milky Way. And it's called a Milky Way because it basically looks like a milky band across the night sky.
Via Lactea.
Yeah, and you're literally looking at millions of stars, billions really, but you're not getting the light from all of them obviously, because our eyes aren't that sensitive, but they're there, which is really cool, and we know they're there because science is awesome. But if you instead think about when you're in the disk and you look up, you don't see as many stars because you're actually looking out of our galactic disk. And so that actually becomes really important when we're pointing telescopes, because it allows us to see what the rest of the universe looks like without all of the dust and junk in our own galaxy that can block the way from seeing all of that stuff that we've seen in much more distant parts of the universe.
So why is the night sky dark then if there's so many stars?
Yeah, so this is actually a really fascinating question. And so the first person that really, it's been cast as O'Blair's paradox, right? Why is the sky dark at night? And you think, well, one way to ask it is, why are there so many stars? But the other is to ask, why are there so few stars? Right? And so that would be the question that's posed by Ober's paradox, is really, if we look out in the universe, maybe we should see more stars. And you may think that's kind of an odd question to ask, but if you think that the universe didn't have a beginning, and therefore it's as old could be, and in science we usually say that it's infinitely old, to give some precision mathematically to that concept, but it has no beginning, and if it's infinitely large in space also, then any direction in the sky we look, there should be a star. And so that's not the case.
Exactly.
And so then we have to ask, well, what are the assumptions we put in to thinking that there should be stars in every direction, and that are the two things, that the universe is infinitely old or infinitely large. And so there's a resolution to this paradox, which was actually first posed by Edgar Allan Poe, of all people. Huh. So even poets can think about astronomy, very constructively, in fact.
The Raven.
Yes. And so he suggested that maybe the universe is not infinitely old, and that it has a finite age, and therefore there couldn't be a star in every direction, because there had not been enough time for stars to form in every direction in our night sky.
Cool.
And so it looks dark at night.
Nevermore.
Yep.
Very good.
Yes.
Awesome. Let's bring it back down a little bit from the cosmic, from Ober's paradox, down to doing observations of what the night sky looks like on Earth.
Yes.
So I suppose you just walk outside. And how do we orientate ourselves? You mentioned the celestial sphere,
yes.
and how does all this relate? As I'm walking outside and I'm looking at something, where does all this come in?
Yeah, so we can talk about the zenith, which is the point directly above our head.
Okay.
And what we usually do, we'll describe the altitude and the direction of stars in the night sky. So the altitude would be the point above the horizon, so the zenith is at 90 degrees altitude.
Okay.
And the direction would be, if we're pointing, I don't actually know which direction I'm pointing in, so I should look at the stars so they can tell me which direction I'm pointing.
There we go. We'll say west.
I'm pointing west. I have to think about it for a minute when I don't have the stars as a reference point. So when I'm pointing west, I can actually tell the direction that I'm pointing in. So we would talk about where the stars are on the night sky based on their direction relative to our horizontal, and then also their altitude, which is the angle they are above our horizon.
Okay. So when you're out there, can you see the whole celestial sphere?
No.
Or do you only see...
You can never see the whole celestial sphere, because we have the Earth under our feet, and it blocks the bottom half of the celestial sphere. So at any point in time, you can actually only see half of the celestial sphere.
Okay.
And that depends on where your location is on Earth.
Okay. So we have this celestial sphere. Are the patterns of the stars as they go on that celestial sphere, is it complicated? Is it simple?
It's actually simple, which is why the celestial sphere is a useful concept to think about in the first place. And stars basically move east to west on our night sky, and they rotate basically in straight lines on the celestial sphere. So if you think of, in a circle. So if you think about those little dots we tacked on the celestial sphere, they basically move exactly in a circle.
All of them?
Yeah.
Well, that's very simple.
It is very simple.
Then how come it looks so complicated?
It looks so complicated because we're tilted relative to the celestial sphere. And so
tilted.
we don't always see the same parts of the celestial sphere.
Okay.
And by tilted, I mean that the Earth is actually inclined on an axis relative to the celestial sphere.
Okay.
And so your altitude, your zenith, that 90-degree angle above your head, is not always lined up with the celestial North Pole. From where you're observing. So if you're standing at 40 degrees latitude, you'll be able to have that exactly above your head. But anywhere else on Earth, it's not going to be exactly above your head. And so you'll see different motions of the stars, depending on where you are.
And then, of course, it depends where you are on the surface of the Earth.
It does.
Right? For example, if you're here in Phoenix, your zenith will be different than if you were at the North Pole.
It will be. And that actually plays an important role in what stars you see. So if you're located at the North Pole, you'll always see the same stars, no matter what time of year it is. But if you're located at the equator, you see different stars depending on the time of year, because your inclination relative to the celestial North Pole is changing.
Okay. So I'm here in Phoenix, and we're here in Phoenix.
Yeah.
And I'll look, for example, toward the direction south. And I will see stars rise.
Yes.
And I will see stars reach some maximum height above the horizon, and then they will set. And I guess that's the circle part of every star, just doing a big circle on the celestial sphere. But then when I turn the other direction and I look like north, there'll be some stars that apparently never rise or set.
That's right.
What are those?
Those are the ones that are circumpolar stars.
Ah.
And they always stay in your night sky because they're very close to the celestial North Pole. You will always see them because they never actually dip below your horizon.
Cool. So we have circumpolar stars, and then we have stars that rise and set.
Yes.
And depending where you are in the globe,
You will see
different ones.
different ones,
For
right?
example, the southern hemisphere.
So if you're in the southern hemisphere and standing on the South Pole, you will not see circumpolar stars that are around the North Pole ever.
Right. You ever been to the southern hemisphere?
No, I have never seen the stars from the southern hemisphere.
Neither have I.
It's very.
I've been twice. I've been twice. Both times I went to Peru, and both times I was there, it was clouded out, and I could not see the night sky. So still in my bin bucket of seeing the sky from the southern
I
hemisphere.
haven't either, and I would just love to. So it's actually really amazing, though, just being here in Phoenix, how different the night sky is from New Hampshire in terms of the stars you see and what time of year you see them and things like that. So that's been kind of interesting.
So along with different locations on the globe, you see different stars. You'll notice that over the course of the year, you will see different stars as well, right? We have the winter triangle, for example, versus which
is one of my favorites.
Right.
It's so prominent.
So what is driving it? How come I see different constellations at different times of the year?
Well, we're on actually, we are moving through space, so we are on that ecliptic plane, and as we're moving, we actually will see different stars in our night sky relative to where we are to the sun.
So the celestial sphere, looks like you've got a celestial sphere there. And we're talking about how you see different stars over the course of the year, how the sun apparently moves through the constellations. You want to talk about that?
Yeah, so here's my celestial sphere. And like we said, when we think about the celestial sphere analogy, the Earth is in the center, and we have this sphere on the outside where the stars are actually located. And in that analogy, the sun is actually orbiting the Earth. So that's not what we know happens in practice. We know that Earth is orbiting the sun, but it's useful to think about the motion of the stars in our night sky using this kind of construction. So the reason that we see different stars in our night sky, depending on the time of year, is actually really easy to explain with the celestial sphere. And so if we think about the motion of the sun around the Earth, we'll notice that the stars that are behind the sun change as the sun is moving around the Earth. So that means that the zodiac sign, because we remember that the zodiac signs, constellations, are the ones that are actually in the ecliptic plane. The zodiac sign that the sun is in, or blocking, changes during the year. And that means that the stars that we see on the other side of Earth are also changing, and those are the ones that we actually see in our night sky.
Great. Hey, did you ever wonder why there are 360 degrees in a circle? How come there's not 47 degrees in a circle, or 112, or 2097? Why 360?
I bet you're going to tell me the answer.
I bet I'm going to tell you the answer. There are 360 degrees in a circle because there are 365 days in a year. That's the orbital period of the Earth. And to go back to our Babylonians, 360 is close to 365, and most importantly, 360 is evenly divisible by 12. So it comes out to be 30, which is the number of days in the 12 months. And so we have 12 hours in the day, 12 hours at night, 12 months of the year, 360 degrees in a circle, all due to astronomy, planetary astronomy, from the ancients, from the Babylonians.
Yeah, so this is fantastic. So many things in our calendar and the way we think about just basic objects come from our night sky.
Excellent.
Cool.
Thank you. So how much does the sun move in a day?
It moves about a degree a day.
Cool.
Which is very interesting.
Right.